So TCP establishes not really bandwidth per se, like a dedicated bandwidth, but it does establish like segment size, right? This is the size of packets we are going to communicate in. And we can establish that because we have a dedicated link essentially through the network, right? So we find our MTU through the network and then we transmit at that size, right? We can establish both those things. What else can we do with the connection-oriented protocol? What other advantages do we have?
Do we know if someone drops the connection?
Yeah, we'll know if somebody drops, or at least if it's dropped elegantly, then we'll definitely know, right? Because we'll get a fin. If it's, if they just go offline, either they're not playing fair or their computer crashes or the network goes down, something, right? Then we can infer that. So how would we infer that?
Is there a heartbeat to the connection?
So there is, but it's through acknowledgments. So when we get into doing flow control and congestion control, we're going to use an ACT clock, and that the acknowledgement clock is your heartbeat. And so, but that also brings into what else TCP provides. It provides reliable communication, right? Because every packet that you get gets an acknowledgement, and if you don't receive that acknowledgement, you send the packet again. So we have a reliable communication that is negotiated for at least segment size. And we have an established beginning and an established end. That actually changes our data model. So that kind of a data model is more like a byte stream, right? So we are going to send a stream of bytes as if they were contiguous across the network, and then when we are done, we'll hang up, right? It's like a communication, right? It's a byte stream that's moving across. So UDP is connectionless. So if UDP is connectionless, what is the contrast between that and TCP?
No need for acknowledgement.
So there's no built-in acknowledgements. Bam, right? So if there's no built-in acknowledgements, it is unreliable.
It's faster.
Huh?
Faster.
It can be lots faster, yes. So it's unreliable, no built-in acknowledgement. It can be faster. Why could it be faster?
Fire and forget.
Because it's fire and forget, right? We can just plug the network up as much as we can, right? Why would, and because we're doing all this, right, it is a datagram protocol, right? We are sending data, which is not going to be acknowledged. That means that missing packets will get dropped and they're not important, right? So in that datagram model, why would we want that? So it seems to, on the surface, at least when I was first examining this topic, right, why on earth would you want an unreliable protocol?
Because you don't care about the traffic.
Because you don't care about the traffic. Or at least you don't care about all the traffic. So, for instance, you're going to do video conferencing, right? It's not that you don't care about the video. The deal is that if the video is late, it's useless, right? If you have to pause the video to get a missing frame to back up, right, then now your whole video conference is now delayed by some bit. And that delay would actually start accumulating, right? The more lost packets, the more delay. And then now you're talking and you're seeing what you're seeing and you're talking and people are receiving your voice now severely out of order with what's actually occurring in real time. So in that case, it is better just to drop the packet, right? It's better to drop 10 packets and actually have like the whole thing pause and know that there's a problem and then it catch back up. Now that doesn't mean that UDP cannot be acknowledged, right? There might be some other interesting information that we could do. We could have a connectionless acknowledged protocol, right? We can have in-betweens, but that really, most of the time, becomes the application layer's problem. So in video conferencing, right, if you're losing packets, what are some of the things that you could do to make it less lossy?
Reduce the amount of information. that you
Sure.
can send.
Yes. Right? We scale it. We scale it back, right? We reduce the video size, right? So we take like a 1900 screen and reduce it to a 700 screen, reduce the amount of color, right? All this other stuff that we could do. We could reduce the audio quality, video quality, and all that stuff. But how could we do that if this protocol is unacknowledged? So if it's just UDP, fire and forget, right? How would the sender even know to do that? So that's when it comes to, you have to build it into your application. You have to build it yourself, right? You're going to have some kind of either acknowledgement, not really acknowledgement, but some kind of feedback mechanism to the sender to say, hey buddy, slow it down. I'm not getting everything. And you would do that in your application, right? So just because we have TCP, which is pretty much, you get everything that's available, and you have UDP, which is basically, it's a fancy word for saying IP, right? There's nothing built into it at all, right? There are in-betweens, but most of the time that is handled by your application. And through the internet, it is almost certainly handled through your application, or is tunneled through TCP or UDP some other way. But if we get on into the class, we'll talk about other things that are more in the presentation level, which we don't really talk about in this class because while it's in the OSI model, it's really nothing for it. But there are things that exist. Some software development kits that give you, something less than TCP but more than UDP.
So what was NetBUI? Was that a UDP? Under Novell, I think it was.
I don't know. That's a long time ago.
It's like port 137 or something.
So anything that's routed across internetwork over IP is either TCP or UDP because that's what the protocol field allows, right? But that doesn't mean that you can't have some application layer stuff that is happening, right, on top of it, at the two endpoints. Remember, when we talked about tunneling, you can pretty much put anything across the tunnel and make it seem local, right? And if you can put anything across the tunnel and make it seem local, then now you can start taking advantage of data link layer stuff that wouldn't be otherwise available, like multicast, right? So those are basically our internet transport protocols. But let's talk about actual implementation, right? So for UDP, UDP is a fire and forget. It is basically IP. So we've been talking about our IP looking like this, where it's data, IP, data link with the trailer, right? So now we're actually talking about this here. So let's get inside of what data actually is. So now data, again, right, is we also have application data, whatever that be, video, whatever, right? And for UDP, right, we're going to have a header. This is now transport. And in this case, UDP. Well, what's the UDP header look like? I just told you that it was basically IP with a glorified version of IP, right? So the UDP header looks like the IP header. It's like a shortened version of the IP header, right? So destination, source, it's like protocol 17. Might need to look that up to make sure, right? And then checksum.
Isn't it length?
Huh? Oh yeah, no, yeah, we have a link too. We have a link in there too. But it's basically a dumbed down duplication version of the IP header. The question is, why does UDP need an IP header? That seems counterintuitive, like we're breaking the model. And it comes down to is how do we implement UDP? So UDP is a fire and forget. So fire and forget means that, hey, we're going to build a socket. And so we'll call so we're going to have to call socket, and then we're going to have to do what? We build a socket, what do we do? It's fire and forget.
Bind it?
Huh?
Bind it?
On the server side, we'll have to bind. What else?
Send or receive.
Send and receive. All right, so let's talk about what each of those are from an implementation standpoint, right? So we kind of have a universal API for building sockets through all the operating systems. Because we want the design of UDP and TCP to function across the internet, right? So we have to have some kind of API on the other end. So we call socket. What does socket do?
Create a channel?
Huh?
Doesn't it create a channel link?
It secures the hardware resources to allow us to access the network. Right? And there might be a lot of software configuration with that, i.e. your source IP address, right? But there might be some other stuff that goes along with it. So that's what socket, hey, I want to use a network card. That is what socket does, returns a pointer for that network card. It will, when we get into actually doing sockets, particularly in your project, all sorts of other neat things you can do with it. Set out timeouts, hint, hint, which will allow you to do things like create a connection-oriented protocol with UDP, right? So what else? So that's what socket does. It acquires the resources, gives you a pointer, and then what does bind do?
You have to bind it to a port.
We're going to bind it to a port. We only do this on the server side. Why don't we do this on the client side?
Because it's
Because it's fire
fire and forget.
and forget. So when we do this on the client, we don't do this on the client because what you're going to do is inside of our UDP, we have a destination and a source. We're also going to have a destination port and a source port. We're going to stick that in there. So what that allows us to do is the server is ostensibly, at least the model says that, hey, the server is going to operate on a well-known port. For HTTP web traffic, that port is what? 80, right? So these are those, or 80. And then we have many, many other well-known ports. What is HTTPS?
443.
443. What other ports do we have? They're very well known.
53.
Which is?
DNS.
DNS. What else?
67.
Which is?
DHCP.
DHCP. right? So these are the services that run, and there's literally a port number. So in our web browser, we type HTTPS, but our browser knows, because we're going to go to HTTPS, to expect not only the HTTPS protocol, but also go to port 443. You can actually change that in your browser. So you can actually say, I want to go to port 8080, which is common for alternate web port. So if you had two web servers running on the same machine, they have to be bound to two different ports. They can't both run on port 80, at least not on the same network card. Right, so we bind and we just basically assign a port. In a lot of APIs, that port can be done via an enumeration, where it just says HTTP, right? Because presumably we don't want to have to remember what all the ports are. So those well-known ports, I believe it now goes to 2048 for the well-known ports. It used to be 1024. Don't quote me on that one. It was definitely 1024 at one point, but I ran into some issues having to run as administrator for anything under 2048, so I assume the standards changed somewhere. And basically, most of the time in operating systems, if you want to bind to a port that's under that threshold, the well-known port threshold, you have to run as administrator most of the time. But that's just implementation details. So that's bind. And then what do? We fire and forget. Send to, receive from. So because we are sending to, we don't have it, so in nowhere in here, either one of these, did we say what IP address we're going to send to? Right, when we look at TCP, we're going to actually tell socket what IP address we're going to send to, and then that, because we've already told it and the socket is set up for that connection, then we just send. But now, we're not doing that, right? We just said, hey, give me the thin and light version of your socket, and now we're going to designate what IP address we're going to send to. And we're also going to tell it what port. And then we fire and forget. And then on the server side, we're going to have a receive from setup. So let's take a look what that looks like. So in the typical client server, right, we're going to call socket over here. We're going to call socket over here. And then we're going to call bind, right, because we need to have a port listing. And then what do? On the server side?
Accept.
Huh?
Do you have to do an accept as well?
Nope.
No, that's TCP.
Just receive from.
Okay.
And that will basically be a loop, right? So presumably if, right, in a very simple one, it might just be a loop on receive from. We're not having any send to, right? So we're just gonna, like, let's say you manually set up two sockets with Netcat, right? And you're gonna push a file through unreliably through UDP, right? In that case, it would just be receive from, right, until there's a control C somewhere, right? But most of the time, there's also a send to, because what you're looking for is some kind of, if you're usually asking the server for something and they reply back to you. So on the client side, we're going to do what? We're just going to do send to and receive from. In some kind of loop, most of the time. Now, when you're programming this, it's not quite intuitive Which one is the blocking call?
Receive from.
Receive from is the blocking call. So when you're if you're looking in this in order, right? So you have socket that's called twice, right? And that could be in either order. And then bind, right? Which has to be before the socket. And then receive from has to be the next call. If there's not a receive from for the next call, what happens? So let's say that send to over here in our client side, remember, presumably these are running on different machines, but you could test it on the same machine, and you could actually test it just writing to shared memory, right? So if you call send to first, before the receive from, it goes across, and what happens over at the socket from the server? It just drops the packet, right? It's like, I have no receive from, and it just drops it. So now what happens is when receive from calls right here, and now receive from is also called here. Both of them are blocking, and you have a deadlock. Now, obviously, this is not a good situation because we could come up with we could even program it correctly where the socket is called first, right? And then bind is called second. And then receive from, which is bad drawing here, is called third, right? But we could come up with scenarios where the send to was dropped. Remember, it's fire and forget. And then now we're sitting on 2 receive froms. So this is what happened. This is what, when we run into this, normally is we need to set a timeout inside of socket to tell it, hey, wait so long, and then unblock that call, and then let it, because most of the time that's programmed in a loop, right? And let it run through the cycle again. Which will be very useful in your project. Because you can just set timeouts now. And if you can set timeouts, because even this, right, even if these returns are actual data, right, the model is no different from an acknowledgement. In fact, in real life, acknowledgements are almost always sent with data. So what's TCP look like? Well, we're going to add some new calls to TCP. What are our new calls? One of them is accept. Already mentioned that one. What other one are we going to do? Another one.
Connect.
Connect and accept, and then we'll also have a listen on the client or on the server side.
Accept, connect, and what was that one?
Listen. All right. So we're going to have socket, socket. And let's build the actual handshake model, and then we'll figure out where the actual calls are, right? So, how many people have heard of the three-way handshake? Who's not heard of the three-way handshake? All right. So a three-way handshake is how we establish a connection. And we'll get into why it has to be a three-way. Because it prevents some very unlikely errors, extremely unlikely errors, but also prevents shenanigans, which manufactured errors, right? So what we're going to do is, remember, the client is usually the one that initiates the connection. Ironically, if you build the actual state machine for this, it doesn't really matter. Even if they both simultaneously try to connect and both think that they're the client, it still works. But, so we are going to send our first part of our handshake, right? So, we're going to ring their phone. Say hello. And then the socket is going to reply by saying, hello. And then this is going to say, can we talk? So, what this really looks like, if you look at the packet, is that we send a synchronize, commonly referred to as a SYN, over to the socket, right? The socket will send an acknowledgement and a SYN, and then the client will send an acknowledgement. Now we send some other data with it. Remember when we talked about out of order packets and we talked about doing stop and wait protocol and ARQ and all that stuff, we needed a sequence number for that to work. So we're going to send, with our send, we're going to send a sequence number. Let's just call that one X. Now by definition, a SYN exists as 1 byte in our stream, and an ACK exists as 1 byte by definition. So what we're going to send back is this acknowledgement is going to come back with an X plus 1. But the socket is the server is also going to send back a sequence number, a different one. It's going to have its own sequence number for data traveling that direction. So that will be Y. And then of course, if the synchronized Y coming this way comes back, what is the acknowledgement this way? Y plus 1. Now before, when we talked about ARQ, we just incremented, right? So the sequence number went, 2, 3, 4, 5, 6, 7, 8, back and forth, right? So that we'd have this synchronized. In TCP, it actually increments by your byte length. So this is why we have to have definitions of SYNs and ACKs as a length of 1. Because we might have a bunch of weird byte lengths with different paddings and all sorts of stuff, right? So we just define it as 1. And then our data packet, when we send data packets, if we send a 1500 size data packet, it would be X plus 1500, right? The current state of X, whatever it is, plus 1500. Now, the question is, why do we have to do all this? It seems a whole lot of work. What errors are we trying to prevent? Yeah, so this is our connection, right? We haven't sent any data yet, right? So imagine some of the errors that could happen. Well, it is extremely unlikely that this would happen in the network. It does happen where, for whatever reason, a bad router, some bad programming, right, packets can be duplicated. So imagine if you had a server sitting here and you have like this duplicated packet that spins around the network, right, and arrives here, and it is a SYN X. So if I get a SYN X in this one, what happens? Well, I get this, right? I get a synchronized Y ACK X plus 1. Right? So the client didn't send this packet. Right? And so what is it going to do in this situation?
Reset.
Just drop the packet. Now imagine that we have a duplicate packet up here. Some previous session, we have a ACK, and it would be Y, but I'm gonna say it's like Y prime because it's not the same Y anymore. So this is why we have the three-way handshake. So while this is extremely unlikely, two duplicate packets show up in the network, and what basically the server receives what it would have been a valid handshake, right? This Y won't match, this Y prime won't match the Y that is sent back here, right? And of course the client wouldn't say anything because it drops the packet because the X is not correct. If we got rid of basically this synchronize and we just did increment X everywhere, right? Then this would work still. And then you would establish a connection that doesn't exist. This is an extremely unlikely error. I don't know how many trillions of times things have to go on for that to happen. But it's possible. But it's certainly possible with shenanigans. Right? So we manufacture some packets and put it on the network to hijack somebody's connection. And we just do replay attacks, right? To get information back. So this prevents that sort of attack, prevents that sort of error. So we have a three-way handshake. It is synchronized with the sequence number, acknowledged with that sequence number plus 1, plus a synchronized with a new number, and then acknowledged with that plus 1. And then we have a connection. And then we send data and we increment the sequence numbers by however much data we send. And we will get really into it when things fragment, how they get put back together, if things are set to don't fragment, and how all that works, right, as we negotiate, and how we use an ACK clock to actually determine when we're going to send those packets for flow control and congestion control. So, we have an established connection. How do we kill it? Right, we got to hang up also. So how do we kill the connection? Well, we kill the connection by sending it a fin, finalize. And then we have an ACK. We also have another fin. We have an ACK. That's the basic setup. Of course, we're going to include sequence numbers again. Why would we include sequence numbers? If I didn't include sequence numbers, what could go wrong?
One of the acts or one of the fins could be some other connection.
Yeah, yeah, it could be some other connection. Yes, right. I could spoof people's packets and also kill their connections by spoofing packets. Remember, if packets are at the sending location aren't well checked, once they're in the network, right, after the second router, they have no idea where they came from. Right, so if I can get past that first check at Comcast of sending a bad packet with a bad source address, right, then I'm off to the races in the network at that point. And so I can assume your IP address if I get past that check and send a fin, right? Because I don't like you, and so I just start sending fins to every place that I think you're gonna go to. And then you can't make a connection ever, and it's very irritating, right? So what we do is we send, what? We send fin X, right, with our sequence number, the current state of X. It's not X when we started, it's X where we are now. And then we acknowledge with X plus 1, but we also send a fin with Y, the current state of Y, and we acknowledge with Y plus 1. So why the double fins?
For the same reason that the three-way handshake?
Huh?
For the same reason. that we-
Sort of the same reason as the three-way handshake. So while this is technically four-way, the reason that it's done it doesn't have to be done. It could be a three-way fin. But if you go through and you're looking at being able to receive finalize anywhere, right? Then it's usually better to just do it in four. That way you don't have programmatically it's just easier. That's the only reason. It doesn't mean that they can't be combined. There actually is a packet that has a FINAC, right? You can send that packet. That's not a problem. The problem is programmatically, most of the time it's easier to do it before. Because you can receive a finalize whenever, right? So think about a TCP. So not like a web transfer, right, where there's certainly some kind of clear boundaries of beginning and end, but think like an SSH session where it can just end at any point. Right. So in order to accept those whenever, it's just, if you look at it, it's programmatically easier to do it for. So in the network, most of the time you'll see them at 4. But for a web transfer or something that has a clear, predictable, begin and end, then you might see a FINAC, but it doesn't really matter. But we do the same thing, right? And this allows us to prevent for very unlikely errors, but also prevent for, being able to hijack somebody's session, or in this fin case, of kill your session over and over and over again.
Does a reset packet have acknowledgement set?
I have to look on that one. I don't know. I don't think a reset gets acknowledged. Also, recognize that this is everybody playing nice too. If you look at actually, so this is everybody playing nice to the standard. There are some software packages that don't send fins. You're being nice to the server when you send the fin, right? You don't technically have to do that, and you get all the information you wanted. And it just leaves their queue. So after some time, the servers had built-in timeouts for sockets, right? So the socket, hey, I haven't received any information in 30 seconds, I just kill it. Because otherwise you're tying up ports. And then you could basically imagine if you're doing an attack and you basically, there's a lot of attacks that used to work well, like doing a send flood, right? Do a synchronize with it and then have a half half handshake, right? And when you do that, you're tying up ephemeral ports on the server side, right? Because these are, right now we are just doing, like, you communicate over port 80, now the server's always communicating over port 80. What really happens is there's a short little handshake, and then you get moved to a different port to do the actual communication. Right, so you can imagine that if you're spamming out doing half handshakes or not finalizing, you do a real connection and you don't finalize, and you can do all sorts of things mean to servers. Right, so in implementation, you have to account for people being not nice. And that doesn't always mean hacking, right? It could just mean not writing to the standard, which is you have to send a fin when you're done. I imagine that there's a lot of working TCP assignments that have no fins in them, right? Because it would work, right? All right. So that's our handshake model. Then we talked about, oh, I just erased it. We haven't done that. All right. So on Wednesday, I think we'll cover some rudimentary TCP stuff and possibly flow control. Actually looking like what TCP, because right now we've covered the handshake, right? Which is establishing a connection. There's a lot more to TCP that's going to happen underneath, which is basically figuring out what size of segment we're going to send. Right? So before with IP and the network layer, we were talking about packets. Now we're talking about segments and getting closer to the actual data that the application sent. Right? So now we'll figure out what size segments we're going to send. We're going to figure out when to send them, which is flow control, based on how fast the client can consume packets. And then later on we'll get into congestion control, which is how fast the network can consume packets. And we'll use an ACK lock for both of those. Yeah. So any questions on today? How far, we have one assignment turned in. How far is everybody else's assignment as far as the project?
The project, I don't know.
Huh? The project, yeah. Don't wait too long. It takes a lot more time than you think. A lot more time than you think. And don't do the TCP one thinking, oh, that was really quick. The UDP one's got to be easier. The UDP one's the hard one. The TCP one can be done 20 minutes. The UDP one typically takes between 10 and 20 hours to get it right. And the deal is probably been a while since you took C, and even if you took it with me, it's been a while, and it's really hard to debug because the information you're sending is over the wire, So the normal debug methods of doing like printfs and stuff only cover like maybe 30% of the issues, and you'll have data that doesn't arrive. You'll have data that is like concatenated with other data, and it's out of order, and it's binary. So there's some tricks on. You should test your file, or test like a file transfer with something that's very human readable and ordered. So what I would do is no kidding, I would make a file that said 1 new line, 2 new line, 3 new line, right? And make that 50,000 lines long, and try to transfer it and make sure all of it transfers, right? And then the next file I would do is get in a hex editor and make like 1 and then space null new line, right? And put real zeros in there, not ASCII zeros, real ones, right? And make sure that transfers. Make sure that your transfers can account for, make the file big enough where it takes more than 1 packet. Because some of the errors happen because you have padding in a packet, or you're reading in wrong things. And so try all that. I can tell you how I'm going to grade it is I have a PDF that definitely doesn't exist on any byte boundary that you guys are going to guess. And so i.e. it's going to be an odd number for sure. So it's definitely not going to be some power of 2. And it's going to be transferred to more than 1 packet also for sure. And I just MD5 the 2. So if the MD5s match, yay, you did it right. So also do that. So when you get the file across and you think it's right, MD5 it and make sure it's right. Because sometimes you'll have like nulls at the end, which in many instances don't affect the human readable version of the file at all, but it will be a different MD5 for sure. And do that. And then I think I told you that the UDP stop and wait is also go back in with just n equals 1. So if you do go back in, or stop and wait is pretty easy, right? It's, send a packet, get an acknowledgement, send a packet, get an acknowledgement, right? Go back in is send n packets, so send 5 packets and get 5 acknowledgements at the same time you're sending packets. So. All right. But don't wait forever for that project. It's way harder than you think. Particularly if you haven't programmed C for a while.
It's basically laid out. You just program the C, test it, make sure it's gonna run, and then MD5 it, make sure it runs.
Yeah.
Do it for TCP and UDP.
And UDP. It's just you gotta add, you don't have to make UDP connection oriented. That's going the extra mile. But you do have to have acknowledgements to get reliable communication. Remember, connection and reliable, while in the terms of TCP and UDP, or connection and reliable are the same thing because TCP provides both of those. There are many applications that do reliable UDP without connections. And we'll probably get into some if we get to that far in the class. Your autonomous cars use reliable UDP. Connectionless reliable UDP. All right, that's it.